Hello everyone, welcome to another video out course. In this video, we are going to solve the problem number 14 and 15. So let's solve these problems together and learn the points of these two problems. So, problem 14. An inductor is made of two coils A and B having 350 and 150 turns. The NA and NB are given here. The coils are wound on a cast steel core and in directions as shown in the figure. So the material of the core is cast steel. We have the BH curve of the cast steel in this figure 7 of the chapter 1. The two coils are connected in series to a DC voltage. Yes, the value of the current for two coils is the same. So A determine the two possible values of current required in the coils to establish a flux density of 0.5 Tesla in the air gap. So how we can calculate the amount of the current, right, for the coil A and B to build up 0.5 Tesla in air gap. We don't have any information about fringing or leakage flux, so we can neglect those effects. So to build up 0.5 Tesla in air gap, we have two possible values depending on the type of connection of the terminals of the coil A and B. So this is the case 1. Okay, here is the structure of the problem. Let's connect this terminal to the positive side of VDC, and we can connect this terminal to this one and this terminal to the negative of VDC. So in this case, the direction of the current is in this direction, this one, and finally this one. So let's check the magnetic field generated by the coil A and the coil B. The coil A generates a flux in this direction, okay, in this direction. And the coil B generates a flux in this direction. So the flux generated by the coil A is in the same direction of the flux generated by the coil B. So we can draw this equivalent circuit, this magnetic equivalent circuit. Yes, so we have summation in the values of the magnetomotive forces. And if we use this equation, integral of h dot dl, that is the summation of Ni for all coils. And if we consider this integration path in the middle of the core, we can write H inside the core, considering uniform fields, average values. You know these concepts from the previous problems that we solved also with ANSYS Maxwell software. And this is the length inside the core. The length of the average flux line in the core plus H gap times L gap. This is equal to NA times I. The value of the current is the same for the coil A and the coil B, plus NB I, right? So we know the value of the LC is given here. You can see the dimensions. The average value is 4 times 8. Yes, we have the same width for the vertical limbs and the horizontal one. So only we can consider one reluctance for the core, and this is the air gap reluctance. The thickness of the air gap is also given here 0.15. Okay, and we have these two parameters. So what about this one and this one? The value of the HC should be interpolated from the BH curve. The aim is to build up zero point 0.5 Tesla in air gap. We don't have fringing, so the value of the core flux density is also zero point 0.5 Tesla, and we should interpolate the value from this graph. So let me copy this. Here we have this graph, okay? And if we are going to have 0.5 Tesla in the cast steel material, the value of the H should be 350. So this is the value of the H core. 350 interpolated from the graph. Henry, ampere per meter. So we interpolate this value from the graph considering the value of the B core equal to 0.5 Tesla. And what is the value of H gap? The value of the H gap is B core or B gap divided by mu 0. So we can calculate this variable also. We have NA, NB, and finally, using this equation, we can calculate the current, right? For the coil A and the coil B to build up zero point 0.5 Tesla in the core. This is the case 1. But what about the case 2? This is the case 2. And in the case 2, we have these connections. We connect this to the positive side of the DC voltage and connect this terminal to this one and connect this terminal to the negative of VDC. So this is the direction of the current for the coil A, and this is the direction of the current for the coil B in this direction. So here is the magnetic field, the flux generated by the coil A in this direction, but the flux generated by the coil B is in this direction. So these two flux of the phase A and B cancel each out. Then we will have this equivalent circuit. The sources are in opposite direction. Okay, so in this case, the integral H core L core plus H gap L gap is equal to NAI minus NBI. So we can calculate the required current in this case. So here you can see Depending on the type of the connection, we have two possible values for the current, right, to build up zero point 0.5 Tesla in air gap. So here in MATLAB, we have this M file for problem 14. This is the magnetic permeability of the air. This is the number of turns for the coil A, the number of turns for the coil B, the air gap length. This is the average length of flux line in the core, 4 times 8 minus L gap. Okay, 4 times 8, we have a square here, and this length is equal to 8, right? 4 times 8 is the perimeter of this rectangle in center of the core. This is the value of the magnetic field intensity in the core interpolated from the curve considering B core equal to 0.5 Tesla, and this is the H gap, 0.5 Tesla divided by the mu 0. So here we have these two cases, the case 1 and the case 2, H core L core plus H gap L gap. I multiply this summation by 1 e minus 2 because the unit of the length is centimeter here, divided by NA plus NB for the case 1, and this is for the case 2. So let's run the code. Here you can see the value of the current for the case 1 is 1.41 ampere, and this is for the case 2. As you can see, the value of the current in the case 2 is higher. What is the reason? Because the generated fields are in opposite direction. So in this case, we need more current for the right phase A to overcome the field generated by the phase B and construct zero point 0.5 Tesla in air gap. So this is the solution of the part A. You can practice that. And now let's calculate the value of the self inductances LA and LB of the two coils. Neglect magnetic leakage and fringing. Yes, the assumptions that we have to draw this equivalent circuit correct. So, how we can calculate the self-inductance of LA and LB? The concept of inductance, as you remember from the electromagnetic course, is a complex concept. Okay? Inductance depends on the level of the excitation, or actually the material properties, depending on whether if we have a hysteresis loop or a normal magnetization curve. It depends on the relative position of the coils, as you will see in the next chapters. For a rotating electric machine, the inductance of a coil depends on the rotor position and so on. So in general, we can write for this example that we have a static case. Okay, let me write here. For this example, suppose we have this direction of the current for the phase A. This is IA and this is IB. So we can write the flux linkage to the phase A is a function of IA and IB. Okay, so we know that the level of the excitation changed the amount of the flux linkage. We can consider, right, any material here, a material with a constant magnetic permeability or a nonlinear magnetic permeability. So for the first case, let's consider a simple version. I am going to consider a linear BH curve. This is H, this is B. Okay, so this is one equation that we have. The next equation, the structure here is static, and the relative position of coils, right, is fixed. And this is lambda B. We can write it is a function of IA and IB. So yes, how we can calculate the flux linkage to the phase A and the phase B? We know that if we consider this phi, okay, this is the flux in the core, and lambda A is NA times phi. Lambda B is NB times phi. So here I consider these directions, right? This field is in the same direction of this field. And how we can calculate the phi? Using this equivalent circuit, this magnetic equivalent circuit. So we can write the value of the phi is equal to the total magnetomotive force NA IA plus NB IB divided by the reluctance of the core plus reluctance of the gap. Okay, so this is the value of the phi, the flux in the core. And you know, this equation, if we multiply it by NA, we will have this equation. We can write lambda A is equal to NA to the power 2 times IA divided by the reluctance of the core plus reluctance of the gap plus NA NB IB divided by the reluctance of the core plus reluctance of the gap. Similarly, for the lambda B, we can write this is NB N A IA divided by the reluctance of the core plus reluctance of the gap plus NB to the power 2, okay, reluctance of the core plus reluctance of the gap times IB. So you remember this matrix equation, the lambda A, lambda B is equal to, this is the LA self-inductance, this is the mutual inductance of the, right, this is BA and this is LB. So this is IA and this is IB. So This is the inductance matrix, like a matrix that we define in ANSYS Maxwell. Okay, so this is inductance matrix, and according to this, we can write that the LA is equal to NA to the power 2 divided by R. R is the summation of the R gap plus R core, the reluctance. And this is LB NB to the power 2 divided by R. And this is the mutual inductance NA NB divided by the reluctance. So we know that the reluctance is not constant for nonlinear materials. For linear materials, the reluctance is constant. This matrix is constant, right? Because the permeability of the core is constant. But for nonlinear materials, no. And this inductance matrix is nonlinear. It depends on the level of the excitation, right? So if we call this L, inductance matrix is also depends on IA and IB. This inductance matrix depends on the level of the excitation. So in this question, we should ask, should we calculate the LA and LB for this level of the flux density in core or not? What is the value of the level of the excitation? Okay, so if we consider this level of the flux density in the core, we can calculate the permeability of the core using this equation, B core divided by H core. Then we can calculate reluctances, and then we can calculate LA, LB, and even the mutual inductance according to definitions that we considered. So yes, this is important point. The inductance matrix is also a function of IA and IB. So here in MATLAB, I calculated the magnetic permeability of the core. The B core is 0.5 Tesla, and the H core, we interpolated it from the graph. This is the cross-section area of the core, 2 times 2. 2 is the width of the limb. Depth of the core is 2. Okay. And this is in meter square. This is the reluctance of the gap. Reluctance of the core, again, for this level of the flux density that we have in the core. If we change the level of the flux density, the value of inductance changes. And here I calculated LA and LB in millihenries. So if I run the code, as you can see, we have LA and LB, right? These two numbers, 34.6 millihenries, and LB is 6.3 millihenries. So can we solve this equation using ANSYS Maxwell to realize the value of inductance for the phase A and B to learn this concept, right, in deep? Let's generate the model here. I add a new 2D design. Let me save the model. Okay, this is problem 14. And like before, we can generate the geometry of the core. The total right width of the outer rectangle is 6 plus 2 plus 2, that is 10. And this is 10. This is another rectangle, rectangle 2. This is 2 and 2 centimeters and 0. This is 4, 4. No, no, excuse me. This is 6 and 6. So select these two, subtract, save, and we should generate the air gap. As you know, like before, we can set the corner point. This is 5 minus the gap divided by 2. And this is 5. What is the value of the gap? 0.15 centimeter. Here, this is the air gap thickness. And the x size, consider 5. Y size is the gap. So, excuse me, I should cut this, paste this here. Okay, we can consider a higher number here just to subtract it from the core. Select this one, subtract. Yes, you can measure the distance between these two edges to confirm that you generated the geometry correct. Yes, the minimum distance is 1.5 millimeter, right? The air gap thickness. Now let's generate the coil arms of the phase A and B. So this is for the phase A, and here I define the dimensions are arbitrary, not important, just we are going to realize important points. This is for the phase B. Let's select this rectangle, duplicate mirror, and this one, right? Okay, we have these two coils. We can change the colors for a better visualization, and also we should set the material to copper. Okay, so now we can define excitations. Let's consider the case 1. Here I set the excitation. This is 350 times the current, coil current, 1 ampere. Later we will set it. Okay, the direction is positive, and this one, the total excitation, the direction is negative. Again, this one, this is 150, direction is positive. This one, the direction is negative. So we have defined these 4 excitations. You can check the directions. Okay. So we should set the material of this object what material is good, we can consider here. Let's search and this time use another material, HP curve, to check our calculations. So cast iron. Yes. Let's check the permeability is constant. No. Cast steel iron. I want to just use another material. Steel. Yes, let's use this one this time. Okay. Here you can see the HB curve of this material, and we are going to use this. So we defined excitations and the materials we have said. Draw the region again. Consider 50%. And let's select edges to apply the boundary conditions. The zero vector potential. And now we can solve the problem. Okay. We can solve the problem and calculate the level of the flux density in the air gap and in the core, and also we can calculate the inductance of the phase A and B. So let's analyze the problem. Now we can plot the flux lines. Okay, the flux lines that we have here is in air gap and the core. So this is for this level of the excitation. Now we are going to calculate the quantities for the material that we considered in ANSYS Maxwell. So again, I save this as problem 14, modify it like before. So like this one, let's copy the BH data to here. And this is the B core, is the, this is the zero point 0.5 Tesla desired flux density in air gap. So we can use the BH curve and calculate the H core. So let's export the HB curve of the material to desktop, tab format, BH data, overwrite it. This is the BH data. Yes. The last one is 2.58. Yes, correct. So we have this HB data for the material that we considered. What is the value of the H core? We need to use the one-dimensional interpolation. B data, this is H data, and this is desired value of the B core. Desired value for the B core and this is the B core again. Yes. So we can solve the problem now. If I run, what is the value of the current? 1.33. So let's set the value of the current 1.33. So analyze again and check the level of the B in the air gap. So let me draw a line here. I am going to draw a line from here to here and plot the by on it. So from the field calculator, add the b quantity, b, add, this is by. So let's consider a fine mesh size for the iron. The mesh size inside selection equal to 2 millimeter, and also select this edge object, assign mesh on this selection equal to zero point 0.2 millimeter, and run the simulation again. I want to plot the y component of the B on this edge in the air gap. And my aim is to build up the desired amount of flux density on it. So field report, this is the polyline 1, by. Yes, as you can see, this is in the negative direction of the y, because this is the direction of the field. So let me multiply this by -1. Not important. As you can see, due to fringing effect, we have this waveform, right, on the edge, and the magnetic field reduces, right, gradually. The maximum value of the B is close to 0.49 Tesla, right? 0.5 Tesla, the amount that we needed here. So it means that our assumptions, right, are correct for calculation of the current. But again, now let's change the value of the air gap. If I consider 0.5 for the air gap length, what is the value of the current? I case 1 is equal to 4.12. So here I write 4.12, 0.5 for the air gap thickness. So let's analyze. We can compare the graph in this case by our calculation in MATLAB when we have this big air gap. So as you can see, the maximum of the flux density is 0.5 Tesla. So we considered a new case. So now let's consider this assumption. Okay, consider another value for the desired flux density, for example, 0.7. Repeat the analysis. I case 1, this one. So in this case, I assumed that the desired core flux density to be zero point 0.7 Tesla in the gap. Let me change this in the gap. Okay. Here you can see the interpolations, and this is the value of the current. So let's run the simulation again and check the numbers. So here is the waveform 0.68, close to 0.7. A little bit we can consider the effect of the fringing, right? You remember from the previous problems, if we consider the effect of fringing, we can set this equal to zero point 0.7 Tesla, right? Exact. So yes, our procedure is correct. Now let's consider this fraction. I want to calculate the reluctance of the gap divided by the reluctance of the core. So as you can see, the air gap reluctance is 32 times higher than the reluctance of the core. Therefore, the magnetomotive force drop on air gap is much higher than the core. So let's change back to the previous assumption, 0.515. This is the value of the current for the case 1. Okay, the value of the air gap, we can modify it thanks to powerful parametric environment of the ANSYS Maxwell. Yes, we can perform these analysis types. So here is the flux in air gap, and now I am going to calculate the inductance. Okay, here we can define this matrix. I include all excitations. The current 1 and 2 are in one group. For the first coil, 350. This one, these two are in the next group. This is 150, 150. So group 1, group 2. Okay, we have two different coils. The number of parallel branches is 1 for both cases. Now we can calculate the flux linkage and also inductance. If I analyze the problem, we can calculate the inductance of the phase A, B, and mutual inductances. So here in the magnetostatic report, let's generate this data table. As you can see, we have L. This is the components of the inductance matrix. We have 4 components, as you can see. This is matrix 1L, group 1, group 1. This is actually the self-inductance of the phase A. What is the value? Let me clean up all previous solutions and just run the simulation for the last parameters that we have set. So in this case, you can check the value of the self-inductance, 2.4. But we didn't consider the depths. By default, the depth of the problem is 1 meter. We should modify this number. 5 divided by 1 meter. The depth of the problem was 2, excuse me. The depth was 2 centimeter, not 5. Okay. So you can see the value of the self-inductance 48 is the self-inductance of the phase A. So if I run the code, LA is equal to 36. Considering these calculations, the value of the B gap. So did we calculate the permeability of the core correct? Here is the B core. We considered it equal to the B gap. Okay. And what is the value of LB? 6.7 millihenries. The same thing for the group B. Add 8 is a little bit higher. So what about the mutual inductance of group 1 to group 2 and group 2, 1? We know that the inductance matrix is symmetric. So here you can see these two numbers. Actually, we have this inductance matrix LA, LAB, LBA, and this is LB. The inductance matrix is symmetric, right? LAB is equal to LBA. And here you can see the mutual inductance is 19. So let me calculate the mutual inductance also. LAB, this is NA times NB. The value of the mutual inductance close to 16. So this is mutual inductance. So we did assumptions in our analytic formulation in MATLAB and we have differences. Let's check the level of the excitation in the core. So here, if we select the core and plot B, we have non-uniform flux density variation, but in the middle, if we add marker, here for example, the value of the flux density is 0.6 Tesla. Here is 0.65. So we don't have a uniform, right, value of the flux density. So the permeability is not constant, right, in the core. So in this formulation, when we calculated the core reluctance, actually, when we calculated the core reluctance, we considered that the permeability of the iron is the same for all locations. But this is not a correct assumption. As you can see, the level of the excitation is different at different locations of the core. So the permeability is not constant. The value of the core reluctance that we calculated is not correct, and then we have these deviations. But however, right, we have these deviations, but our analytic calculations are still good. How we can be more precise? You know, if we consider this case. So let's clear all these markers, copy image, and paste this here. So if we consider, for example, one reluctance here, one reluctance here, right? one core reluctance here, one core reluctance here, another one here, 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 okay? And we divide the iron core into different parts. For each reluctance, we can calculate the permeability depending on the level of the excitation and solve the circuit. But in this case, we will have this distributed equivalent circuit, right? We have a number of reluctances for the core. This will be more complex. But this is what the finite element software do. We don't need to generate this model. If I generate the mesh, let me select all faces and plot the mesh. Actually, the finite element software do this for us. Each of these triangle is actually one reluctance in our case. And as you can see, the software divided the structure into a high number of reluctances. And we can solve this problem with a good precision. Yes. So now you can get a good idea about what the finite element software do. Why I reduced the size of triangles in the iron for a more accurate solution? Because I wanted to consider more reluctances. Okay, so this size is good, and we can calculate the magnetic field with a good assumption. You can consider other sizes also. Perfect. We have this powerful software, and we can do this kind of analysis to calculate quantities such as B and also the self and mutual inductances. You can change the level of the excitation, calculate the inductance, and check how the inductance changes when we change the level of the excitation. Okay, so now let's go for the next part of the problem. Okay, if the coil B is now disconnected and the current in the coil A is adjusted to 2 amps, determine the mean flux density in the air gap. So here in this case, we only have the field generated by the coil A. This is the magnetomotive force. We are going to calculate the mean flux density, the average value of the flux density in the air gap. So what is the value? Here we have this equation. Na times I is equal to H core. L core plus H gap, L gap. The H core, the value of the L gap is B core divided by mu 0. Okay, we have this one. And in this equation, we have Na times I, we have L core, L gap, mu 0. So we will have this equation. This is equation of a line like the example that we had in the chapter. This is equation of a line, this red line, and the operating point is the intersection of the BH curve of the cast steel with this load line. This is the operating point. We can calculate this operating point iteratively, right? We can assume a value for H and calculate the operating point. But how I can calculate this operating point in MATLAB? Yes, Here, for this modified problem, we have this pH curve. Let me plot this pH curve. So here we are going to solve the part C of the problem. We have this pH curve, I am going to extend this pH curve also for negative values of the H. How we can extend it? We can consider this H data equal to, H1, H data 1. The first one is 1. So here I can write negative of H data and H data from 2 to n. And B data the same. Extend the H data and B data for negative values first. So we will have this pH curve. So why we have something like this? Yes, because when we reorder the data, we need to flip them. So suppose we have this vector in MATLAB 42685. If I write flip from the left to right x, as you can see, we can flip the data. This is 5, 8, 6, 2, and 4. Just we flipped the vector from the left to the right. So this is flip left right of the H data. And the same thing for the B data to construct the this side of the curve. So I need information for both sides, the normal magnetization curve. And what is the load line? You can see the load line here. This is the shift, and this is the actually the multiplier of the H. So let me consider this load line here. We have this HB curve for the material that we selected from the ANSYS Maxwell. This HB curve. We have this equation for the load line, and we are going to find this intersection numerically using MATLAB. This is the equation of the line. We can rewrite this to this equation, B equal to negative of K1 H plus K2. This is K2, right? So K2 is equal mu 0 times NA times current. For the case C, the value of the current for the case C is equal to 2 ampere current, coil A current in part C of the problem, 2 ampere. So this is the value of the K2 divided by the L gap. We should write it here, divided by L gap times 1e minus 2. So this is the value of the K2. And what is the value of the K1? It is equal to mu 0 times L core divided by L gap, the slope of the line. So this is mu 0 times L core divided by L gap. So how we can draw this line in MATLAB? How we can draw it? When the value of h is 0, when the value of the h is 0, the value of the b is k2. So here we can consider these two pairs to draw this load line. When the value of the h is 0, b is k2. And when the value of the b is 0, h is equal to k2 divided by the k1. Okay, so here we can plot the load line. So plot 0 and k2 divided by k1, and here k2 and 0. Okay, these two. Let's set the color to red. This is the load line, and if I run the code, here you can see the load line, right? Because here we have a huge data for h. We cannot right draw this load line good, but here I am going to set the value of the x lim of the graph from negative k2 to k2. So now we can plot it better. The get current axis and set the x limitation. Let me check. No, excuse me. K2 divided by K1. This range. So here you can see the HP curve, the data that we have for HP curve, and this is the load line. So we need to intersect to find this value, right? This operating point for the air gap, flux density, and the core. So here, if we only excite the coil A, the aim is to calculate the mean flux density in air gap. So we need to find this intersection point, right? Also, you saw this in the graph. So yes, we have this BH data and we have this load line. Simply, we can use the root finding MATLAB function to find the intersection point. How? We need to define error. Suppose we have this HP curve, right? We exported it from the ANSYS Maxwell to MATLAB, and this is the HP curve that we have for the load line. We can assume this arbitrary value for the h. So we can write this function error, this error function. The input of the error function is h. Yes. So we can assume arbitrary value for h, and according to this load line, we can calculate the value of the b for the load line. Also, we can calculate the value of the b for the BH curve, right? B core or B gap. So in this case, when we calculate these two numbers, we have this difference. This is error, right? We know that the operating point is when the error is 0. B line is equal to B core. So we need to shift the value of h toward this point, or if we assume h here, we need to shift it toward this point to find the intersection point. Actually, this is a zero finding, a root finding problem for the error function. So here I define this function error FCN. The input is h. I call this arbitrary h. This is an arbitrary h. So how we can write it? This is h star. Let's say h star, arbitrary value for h. And for this h star, we can calculate BL, the load flux density. B load is equal to, according to the equations that we had, minus K1 times H star plus K2. And what is the value of B core? We can use one-dimensional interpolation like before. We had this one, but in this case, we have H data and B data here. This is the value of H star. Okay, so we specify H star value and interpolate B core. This is B load. Okay, and finally we can define the error. Error is equal to B core minus B load. N. So to avoid any error, we can consider extrapolations, right? A linear version of extrapolations to have the value of the B for all points. When the H star is here, this is the load line. And when H star is here, the value of the error is negative. And when H star here, the value of the load is, the value of the error, is positive. So when the value of error is 0, we can find the operating point. So how we can use the root finding function in MATLAB? I am going to explain it now. We have a variety of the functions in MATLAB. For example, f min bnd. This finds the minimum value of function, right, for a specified range, x1 and x2, the minimum value of a function. Or we can use f0 function. So this finds the root of a function using x0. So here you can use different versions, different functions, no problem. Here, because I used this function at the end of my M file and I need to know the value of these variables inside this function, I change this M file to a function file. So just let me delete this, and here I write the function. The name of the function must be the same as the name of this M file, and here we can end the function. So in this case, As you can see, the color of this variable changed. So because this is a nested function, and in this case we have access to all variables, right? When you define a function in MATLAB, and you can define also a nested function, a function inside a function in MATLAB. And when you define variable x here, for example 5, this variable is also available in this function and you can use it, right? This function knows this variable. This type of coding is very good and we can use it effectively in our code. So here, let's use the f0 function, the MATLAB f0 function, to find the error of this function. We need the function handle. Also, when you use the f0 function, you can specify the starting point. Let's consider the starting value for the magnetic field intensity H star equal to, let's say, 1000 here. The output of this function is the H. This is the H operating point. The intersection. Let's write the H of the intersection. And finally, we can use either the load line, this one, to find the value of the B of intersection, BI. This is the intersection point of the B. We need H intersection. Yes, we use the f0 function to find the root. Then we calculate the HI and BI. Then we can display HI and display BI. So let's run the code. What is the error? Invalid character. Here, excuse me, this is linear and this is extrapolation. So let's run. As you can see, the intersection point, the value of H is 231, and this is the value of the B, 0.52 Tesla. So here you can check the intersection point, 0.52, 231. So yes, we calculated the value of the H and the value of the B inside the core when we set the value of the coil current equal to 2. Let's check this in the software. If I delete the mesh, delete the B, I want to set the value of the current for the phase A only equal to 2 and set the current of the phase B equal to 0. And let's solve the problem. Analyze. In this case, we can calculate the value of the By, and also this is the B in the air gap, 0.52. Okay, 0.52. The same number that we calculated here, the intersection point. We calculated the load line equation, the HP curve equation, and we calculated the operating point. This is the value of the H inside the iron. Let's check. If I draw this path in the iron here, here in the middle of the structure, right? Polyline 2. And if I calculate the tangential value of the h, this time let's select the h quantity, unit vector tangent dot product. This is the tangential component of the h along the edge ht, and let's rerun the solver. Okay, analyze. So in this case, we can calculate the average value of the tangential component of the edge along this polyline 2. So we can generate this field report, the polyline 2 ht. Okay, this graph. Calculate the average value. So for one point close to the air gap, we have a very big number. This is just again because of the interpolation. Let me select all objects and plot the mesh. So you can see the solution mesh close to the air gap. We know that the value of h close to the air gap is high. So here this big number is interpolated. So we can remove this point. Just let's set the distance, not 0, 0.1. A very right one number, very low number here, 1 millimeter, just to remove that data point, and specify the y range minus 300. You can see the value of the h. When I calculate the average value, that data point in interpolation changed my assumption. I need to calculate the average value for this graph. So if I calculate the average value, not for full distance, just for this range, the number is minus 242. This is 231 in our analytic calculations. The negative sign is not important, so it shows that even our analytic formulation is good, and we can detect the operating point using a nonlinear root finding, defining this error function, defining this load line, and knowing the BH curve. If you didn't understand this averaging, let me clear and repeat the problem again. This is just because of interpolations. Here, let's select this polyline 2, modify the first point of this segment. Instead of 50, let's write 52. Okay, and for this segment I start integrating and calculating the average value from this point, not very close to the air gap, because in air gap field variations are high, and you will see that data, right? That is very high. We know that the h in the air gap is much higher than the h in the core. So if I run this M file, the h in the air gap divided by the h in the core, that is much higher. So you will see that data in the graph. The amount of the magnetomotive force drop in air gap, right, is different from what we have in the core. And for the last line, this one, let's set the position of the y coordinate of the endpoint to 48. Apply. So not too close to the 8 gap. This polyline for calculation of the average value of the HT. So run the simulation again and plot the value of the HT for polyline 2. This is the value of the HT. Now this is better. So negative sign. What is the average value? 242. Great. So as you can see, we estimated this number in MATLAB using analytic calculations and root finding, the F0 function. So as you can see, these manual calculations are good and we can calculate close numbers to the operating point from what we have in the ANSYS Maxwell software. So you can repeat this very important example, calculate the inductance matrix, and realize these important points. I think the time of this video is high, so let's solve the next problem in the next video. Thanks for watching.